أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم سبحانك لا علم لنا إلا ما علمتنا إنك أنت العليم الحكيم. Assalamu alaikum dear students. Today we're going to do the 10th lecture of operating system. So today we'll discuss semaphore. uh, we have discussed how to deal with the critical section problem in the previous two lectures. Those solutions were not only confined to solve critical section problem, but they were also complex. They were not only to solve critical section problem, they were also complex, and they maintain additional data structures and take significant time to decide which process be let to enter and the critical section, right? So before deciding that which process should be allowed to enter the critical section, it needs a lot of calculation and a lot of processing. So these were the four problems associated with the previous solutions that we have discussed so far. So today we are going to discuss yet another solution to critical section problem, that is semaphore. So today we'll discuss semaphore. Semaphore is not only simple in nature, but also used to solve sequencing and multi-instances resource sharing. So these are the additional uses of semaphore. A semaphore is nothing but an integer value that is very strictly used for synchronization. So basically, a semaphore is an integer value, but it is used very strictly. Very strictly, they will discuss later in this lecture. But the use of this integer value is a really tricky one, and it is for synchronization purpose, for critical section, for sequencing, and for multi-instances resource sharing, right? Its initialization, increment operation, and decrement operation are performed through some standard ways to ensure progress, mutual exclusion, and bounded weight. That were the four criteria. They were the four criteria that we had proposed earlier in the inter-process communication introduction. So the initialization of this integer value, that is semaphore, its increment and decrement operation are performed through some standard procedures. Uh, First, an integer variable called semaphore is declared and initialized to 1. So it is nothing but we'll just simply declare an integer variable and we'll initialize it to 1, right? Then only two standard atomic operations can be performed on this variable. Two standard and atomic operations can be performed on this variable. Because of these operations, the variable becomes a semaphore, right? So semaphore is not a separate branch of study, but it is just an integer variable. That variable has two atomic and standard operation. When this variable is interpreted in this context, then we'll call it a semaphore. One is to increment the value and the other is to decrement the value. So the two functions that we are two operations that we said here are basically the increment and decrement value operation. These functions are to increment or decrement the value of the semaphore. The operation or function which decrements the semaphore is called wait. So one of the functions will be wait function, or it can be sometime it is written as p. It is from Dutch proberen. So proberen means to wait, right? So sometimes we will also use a p instead of wait operation, or it is also sometimes called down operation. So the operation through which the value of the semaphore is decremented is called wait, or simply p, or down. The function which increments the value of semaphore is called signal, or v from Dutch verhoeven, or signal. So these are three names associated with the function which will increment the value of this semaphore. A signal operation is straightforward increment, but we must have but wait has some additional testing. Wait is used for entry in the critical section and signal is used to exit from the critical section. So in these two operations, the signal function is nothing but a straightforward increment operation. Just for example, integer c and c++, a function that increments the value, that is c++. A single statement function is the signal operation, a signal function. On the other hand, the wait has some earlier testing, and then it has to decrement the value of the semaphore. Wait is used to for entry in the critical section. When once we are entering in the critical section, we must call wait operation, and once we are leaving the critical section, then we will run the signal function. Consider the definition of the signal function. So here is the signal function. Simple. Signal is a function which takes a variable s, that is the semaphore, and it does nothing but just increment the value of the semaphore, right? Similarly, the wait operation, you can see here, and the wait here is some coding logic. In this piece of code, you can see that here is a while loop, and that loop terminates with semicolon. Such a loop is called busy wait. So it is a busy wait. Sorry. So it is a busy wait, and it never let the processing go ahead. It never lets the processing goes ahead until this condition is true. Once the condition is true, it will loop through the same statement again and again. Once the condition becomes false, then the control will be shifted to the next statement after the loop. Alright. When a system is executing in these functions, then all interrupts are disabled, so they are atomic operations. In the introduction, we said that these functions are atomic operations. Atomic operations means that once a function is executing either in this function or in this function, then at that time, if there is a single processing system, a single processor system, then all the interrupts will be disabled. So at this moment, interrupts are prohibited, and no process can interrupt a process to preempt, right? Similarly, there are two types of semaphores. We'll discuss both of them. One is called binary, which can hold only values only 0 and 1, and counting, that is general semaphore, which can hold any value. So we have two types of semaphore. It means that we have integer, for example, integer s, and if this integer is restricted to hold only values 0 or 1, then we will call it a binary semaphore. But if this is allowed to hold any positive negative value, then we will call such a semaphore a general semaphore or counting semaphore. So let us understand with example that how these functions basically work. So for example, we have 5 processes P0, P1, P2 and P3, and this is the code that a process should execute while true means that as long as a process wants execution. So first it will execute a function, that is wait function, because it is entering in the critical section. As I said earlier, that whenever a process wants to enter the critical section, it must execute its wait function. Once the wait function is executed, and this function determine whether the function should be allowed to enter the critical section or not, then the function suppose the processes enter the critical section, then once they leave, they will execute a signal function that will determine that whether the next process be allowed or not to enter the critical section. Alright, for example, you can see here the code for wait function, and here is the code for a signal function. So these are the two atomic functions or atomic operations that can be performed on a semaphore. Now for example a p naught one execution, and p1 while executing, the first value of s is equal to 1, that is the initialized value, because as I said earlier that whenever we declare a semaphore, its value will be initialized to 1. Alright, and for example p not wanna enter the system, so it must first execute the wait function. Alright, so it must execute the wait function, and once it calls the wait function, then it determines whether the s value is less than or equal to 0. But you can see here that the value of s is not equal to 0, so this condition becomes false. And if the condition becomes false, then it will have to move ahead and do the next step, that is s minus minus, and this way the value of semaphore will be decremented and the control will be returned. So it will generate 0, the new value of s will become 0, and control will be returned to p naught, and p naught should be allowed to enter in the critical section. Alright, now p naught is processing in the critical section, and at this moment, for example p1 and p2, two more processes want to enter the critical system, and for example they enter the system simultaneously. So both of them will have to execute the wait function. But you can see here, as we said, that wait is an atomic operation, so at a time only one process can enter the system. For example, they are competing, so if one process enters the wait function, the other process will wait, because this function is not like other functions in which more than two processes can enter simultaneously. These are special operations, and in these operations, once the process is executing in a wait function, then all other interrupts are blocked and the process cannot be preempted. Right, so now p1, although p1 is in the wait function, but it is in a busy wait, because p1 is in wait function but it is in busy wait, because every time it is checking this condition, and every time the condition becomes true, because s is less or equal to 0, so s is 0 here, you can see, then it will not proceed and it will keep busy over here, and this will be a loop like this one. Right, so p1 is waiting over there, and p2 is waiting outside the function, because is it in wait for a p1 to leave the wait function. At this moment, for example, p naught terminates its critical section and enters its and leaves its critical section, then it must call a signal function. And when signal function is called, signal function is nothing but it has to increment the value of is, which is semaphore. The previous value of the semaphore is 0. Once the signal function is executed, then its value will become 1, and p naught will enter in the remaining section. As I already said that p1 is watching this value every now and then, it is watching the value of s, and as soon as it notices that the value of s is no longer 0, then it will decrement the value of s. It will decrement the value of s, and next value will become 0, and this p1 will enter the critical section, because it has done with everything. So now p1 is in critical section, p1 is in critical section, p naught is in remaining section, and p2 wanna enter the critical section, so it must execute the wait function. So p2 will execute the wait function, and it will fall in a trap. Here is a trap for p2, because you can see that it will check every time this condition, and the condition will true, and once it is true, it will always loop in this statement, it cannot proceed. All right, for example, at this moment two more processes enter the system, but both of them will have to execute the wait function. But if a process p2 any process is there in the wait function, since no other process can enter the wait function, at this moment you can see here that, for example, p1 leaves its critical section, then p1 must have to execute the signal function, and once it executes the signal function, then it does nothing but just increment the value of the s, which is previously 0, now it will become 1, you can see here, and p1 enters the remaining section. As p2 was in a busy wait in this statement, it notices that it notices that s value is no longer 0, so it will decrement the value, and the next value of the s becomes 0. And because the wait function is executed successfully, now p2 will enter the critical section. Now p2 is in critical section. At this moment, for example, p4 also both of the processes p3 and p4 were waiting to enter the wait function, and for example, p4 gets a chance and it enters the wait function, but it once again it also falls in a trap because s value is 0, so it will wait in this statement. For example, P2 leaves the critical section and it must execute signal function. In the signal function, the value of the s will be incremented and the next value will become 1. But P4 was watching this value very keenly, and now it finds that the value of s is no longer 0, so it will move ahead. And once it moves ahead, it will change the value from 1 to 0, and it will enter the critical section because it has done successfully with the wait function. Alright, and now suppose p4 is in critical section and p3 enters wait function, so p3 will wait in the wait function because this infinite loop or busy wait will trap the p3 to keep moving and moving on in this step while p4 is in. Now suppose p4 leaves the critical section, then it must have to execute a signal function. The signal function is nothing but to increment the value of s, so the value of s will become 1, and you can see here that now the value of s is 1, so p3 notices this value. P3 will notice this value that s is no longer 0, then it will decrement the value of s, and you can see here that s value is 0 now, and p3 will enter the critical section. And similarly, once p3 terminates its critical section, then it will call a signal function and other function will be allowed to enter the critical section. So this is how basically semaphore work. You can see how simply they are implemented and how quickly they are used. The only technical thing is that once a process in a critical section, then in a wait function or a signal function, then no other process can enter that section, and our interrupts are disabled in a single processor system. While in multi-processing system, we have other mechanism in which we can ensure that no two processes can execute concurrently in the same function, like wait and signal, by blocking the bus to the memory, just like before we'll move ahead and so on. Now let us discuss another example in which we will discuss the synchronization of two processes with the help of a semaphore. So suppose there are two processes P1 and P2. There are two statements S1 and S1 with P1 and S2 with P2. Okay, and we want to synchronize P1 and P2 in such a manner that S1 is executed by P1 after P2 executes S2. Alright, so actually we are ordering the processes, or we are restricting the processes that this statement will be executed if if some other process executes some other statement. So here we are restricting process P1, that P1 should execute S1 if P2 executes S2. Alright, it means that if P2 has not executed S2, then P1 will not be able to execute S1. Alright, for that purpose, for example, we have P1 a process and P2 a process, and similarly we have a common variable m that's called mutex, or simple semaphore, that is initialized to 0. Unlike the other semaphores which are initialized to 1, here we are initializing it to 0, but we will have make a minor difference in the implementation. And then we will for P1, in the P1 code, we will write a wait on mutex, and then we tell it that execute statement number 1. Similarly, and P2, we will tell P2 that execute S2, but then you will have to call the signal M, and the definition of the wait function is here you can see, while S is less than or equal to 0, so S be and busy wait, otherwise S should be decremented. Now suppose that P1 wanna enter the critical section. P1 wanna enter the critical section. Wanna execute this one. If it wants to execute it, it must have to call the wait function. But once it calls the function, then it will be trapped in this statement. It cannot proceed because it will check the value of m. Sorry, this is not s. It will check the value. You can name anything for variable. Just I have mentioned here m, so I'm writing here m. So as long as m is less than or equal to 0, then P1 will wait here. But for example, in meantime, P2 enters P2 wanna run this code, then first it will run S2 without any condition, without any trap, without any condition to meet. So S2 will be run. Once the S2 is completed, then it will run the signal function, and once the signal function is run, then it does nothing but just increment the value of m, and now its value becomes 1. Once its value becomes 1, then this one is being watched by this function over here, which was waiting for this value, and as soon as it finds that the value of m is 1, so it will decrement the value, that is it will again turn the value of m to be 0. Right, it will again turn the value of m to be 0. Actually I have written here s, but it must be m. Okay, and after decrementing the value, it will have to return back here, and again it will have to execute s1. So in this way we can coordinate the two processes p1 and p2, that p1 executes which statement, provided that p2 executes some other statement, right? The busy wait or Spinlock is the major disadvantage of Semaphore as well as of the previous solutions, particularly for single CPU. Just like in the previous solutions, that is, we normally write the code like while, and then write some Semaphore like in this way, while, and then there is some condition and followed by a semicolon. This is called Spinlock or busy wait. Spinlock or busy wait. This time or this statement wastes significant amount of time for CPU because it keeps a process waiting over there and keeps the CPU busy without doing anything beneficial, even though other processes must wait over in the waiting queue and they need the CPU to do something. But a process once enter the CPU, it waits in here in infinite loop, so as long as the semaphore value is not reset. So this is a major drawback of this solution, the semaphore, as well as the previous solution. One way to overcome Spinlock is to block the process and add it in a waiting queue, and as soon as the process which is currently in critical section leaves the critical section, then it executes a wake up call which not only change the value of the semaphore but also pop up a block process from the waiting queue to execute. So this is another is a solution to Spinlock, that once a process for example executes a wait function and it is turning to be blocked, then it is simply blocked, it is blocked and is put in the waiting queue, and the running process when terminates its critical section, then it not only change the value of semaphore but also make a wake up call. So the block and wake up are two operating system inherited function calls in which the process is either brought to CPU or it is blocked, right? Thus we need to modify the definition of semaphore. Alright, so the previous definition was a single integer, but now we are going to just to enhance this definition, and in order to counter the Spinlock, in our new definition, semaphore consists of a structure with integer value and a list of processes. Now it is a structure that consists of an integer value and a list of processes. The value is semaphore, while the list is whether to enter the critical section or not, right? In the process waiting for the And the list that we have, the value will determine, the value is basically the value of semaphore that will decide which process to enter the critical section, while the list will determine that how many processes are waiting to enter the critical section, or once a process executes a wait call, a wait function, then it is added in the list that is declared by the in the structure. So here is the new definition. The previous definition we said that semaphore is just a variable, but now semaphore is an integer, is a composite of integer value and a pointer to a list, right? So we have a pointer, a data structure that we have declared here. So it is a structure and it has an integer value, and another structure that is of processes, of type process, and it is a pointer to L, pointer to L of processes. In this definition, the value of semaphore can be negative. The magnitude of this value is the number of processes waiting in the blocked queue, waiting queue. In the new definition, in the previous definition we said that value can either be 1 or 0, but now the value can be negative but it cannot be positive. At most it will be 1, but at least it can be -1, -2, -3, so its value can be negative, and the magnitude of that value, magnitude of negative value, will show us that how many processes are waiting in the block queue. The new definition for wait function will be that for wait function we will take a semaphore as an argument, and then we will decrement the value s dot value minus minus, so the integer value will be decremented, and then we will execute this condition. If s dot value is less than 0, then add it to L, add this process to list and block the process simply. On the other hand, the signal process, the signal function is that signal process does that it increment the value, and then it checks the condition that is dot value is less than or equal to 0. If it's the value of s is less than or equal to 0, it means that there are some processes in ready queue, so remove a process from L. So it removes a process from L and then executes a wake up call. So here are two standard calls. The block call just block the currently executing process, while the wake up call remove a process from the ready queue and bring it into the CPU. Now binary semaphore is the one which takes value either 0 or 1, as I've already said, as we saw in the previous example, except the last definition. In the last definition it was not so, right? Counting semaphore is the one whose value can goes on in increasing order, starting from 0 or 1 and then moving onward. The lowest number shows that the process is allowed to enter the critical section, while all other show that the process should wait because some other processes may be running in the critical section. So in the counting semaphore, the least value, we can either set the least value to be 0 or 1. If we set the least value to be 1, then only if the semaphore value is 1, then a process should enter the critical section, and if its value is greater than 1, then it will not be able to enter the critical section. Here is an implementation. In this example we will understand that how it basically works. Counting semaphore is implemented using binary semaphore. Okay, consider the implementation of counting semaphore. How can we implement a counting semaphore? So let's see. So now let us discuss how we can implement a counting semaphore using binary semaphore. So for first we will declare two binary semaphores, right? So binary semaphores S1 and S2. Two semaphores will be discussed. Will be declared. The first semaphore will be initiated to value 1, while another semaphore will be declared initialized to value 0. And count variable, integer count, that will be initialized to 1. That is basically counting semaphore. And here is the definition of cwait. So cwait is a function. Cwait is a function means counting wait. It is different than the wait that we have discussed so far. So counting wait is something different. In the counting wait, first we will execute the wait function. The wait function will be first executed, but this wait is the wait that we have discussed so far, and then it will decrement the value of counter and decides if count is less than 0, then signal s1 followed by wait s2. Alright, so these two statements will be executed if the condition is true, and finally signal will be issued on s1. Here one thing should be noted: the c wait is the counting wait function, while these wait are two standard wait functions that we have discussed so far. Similarly, this signal is the standard function that we have discussed so far. Similarly, C signal will be a function, and this first the wait on S1 will be called, and followed by counter will be incremented, and then if counter is less than or equal to 0, this signal on S2, else signal on S1, right? And here is the code that how a function if a process enters the system, then how it will execute. You can see here that first while true means that as long as a process one execution, then first once it want to enter the critical section, then it must execute cwait function upon the cs. That means upon the count variable that we have discussed here, this one, right? So this variable will be passed and this will be received by this cwait. Similarly, it will enter the critical section if all these functions are satisfied. And here we are three processes, P1, P2 and P3. Note that these are basically the wait and signal functions that we have previously discussed. So these are the wait and signal functions. They are different than C wait and C signal, right? Suppose that we wanna enter the critical section, then P1 must execute a C wait function upon the CS. CS here means the count variable. So P1 will execute this function and it will move to cwait function, and the cwait function at first execute the wait on S1. Sorry, this bracket is not involved in it. So wait on S1. Once wait on S1 is executed, then P1 will move to this function and it will check that but you can see that this wait is on S1. So S1 is basically passed as an argument to this function, wait function, and it will check that whether S1's value is less than or equal to 0. No, the condition is false, so it must not wait here and it will proceed to this one, and S value will be decremented. But now this is basically S1 because actually it was called on S1. So S1 value will be decremented and now the value of S1 will be 0. You can see that S1 value will be 0. And now it will return back to count minus minus, and it will execute count minus minus and the value of count will become 0. Okay, next it will move ahead and it will check if count is less than 0. If count is less than 0, then signal on S1. You can see here that count's value is equal to 0. It is not less than 0, so it will not execute these two statements, but it will goes toward this instruction in which the signal on S1 will be called. So it will go to signal on S1, and signal on S1 will be executed. Here you can see that S1 signal is on S1. So S1's value will be incremented and now S1's value will become 1. Okay, and P1 will return here, there and again in critical section. Now P1 is in critical section, and at P2 and P3 also want to enter their critical sections, so they must execute wait calls. P2 calls, P2 and P3 both call cwait, and now for example P2 enters the wait function on S1, wait on S1. So it checks that whether S value is less than or equal to 0. No, its value is 1, so its value will be decremented and S1's value will become 0. And at this moment P3 also enters the critical section, and but P2 returns to count minus minus. It will decrement the value of the count that was previously 0 and now it is minus 1. Okay, and similarly P3 will block here because will be blocked here because P3 will be an a trap. It will see that S1's value is less than or equal to 0. Yes, the condition is true. If the condition is true, then it will wait there. Again P2 will move ahead and it will check that whether count's value is less than 0. Yes, count's value is less than 0, it is minus 1. So if its value is minus 1, then it will have to call on signal on S1 and wait on S2. So first it will call signal on S1. So if signal on S1 is passed, then S1's value will be incremented and the new value of S1 will become 1, right? P2 will move, similarly P3 will be released now because P3 was blocked due to S1's value. Now P3 is released and it again decrements the value of S1. S1 value next S1 value become 0, and now P3 will move back and it will decrement the value of the count, so that was minus 1, it will become minus 2. Alright, and now P2 will move back and it again execute wait on S2. Now it will go there and you can see that it is now executing wait on S2, but it will always found this condition to be true because S value is less than or equal to 0, then it will fall and trap, and now P2 will be blocked in this particular statement. Let me clear this one first. Alright, so let's move ahead. And now for example P3 will proceed and P3 checks that whether count's value is less than 0. Yes, because its value is minus 2. S value is less than 0, so it will issue signal on S1. So it's once it issues signal on S1, it means that it increments the value on S1. Okay, and you can see here that at meanwhile P1 finishes its critical section and now wanna release the other processes, so it issues signal on CS. So signal on CS will be called and P1 will go here, and this at this point it will call wait on S1. P1 once executed wait on S1, it simply decremented the value of S1. Okay, and now P1 continue moving on and it increments the value of count. So count was previously minus 2, now it is incremented and next value is minus 1. Similarly P1 will evaluate this condition. If count value is less than 0, count value will be checked and that value is minus 1. So if it's minus 1, it will issue signal on S2, and if it issues signal on S2, then it means that it will increment the value of S2 and that will become 1. You can see here. Similarly at meanwhile P2 finds that the value P2 which was waiting on signal 2, it must be remembered that P2 was waiting on signal 2 on S2, and now it finds that S2's value is not equal to 0, so it will continue moving on and it will decrement the value of S2 and that will become 0. Now P2 decrements the value of S2 and it becomes 0, and it finally goes for this statement and it issues signal on S1, but at this moment P1 returns to its remaining section, and now P1 is in the remaining section. At this moment P3 returns and previously it had executed signal on S1, now it must execute wait on S2, and it goes here and it executes a function of wait on S2, but once it see here that the S2's value should be less than or equal to 0, but it is yes, it is true, and if it's true then P3 will fall and trap and it will be blocked in this step. Similarly P2 will proceed and it will execute signal on S1, and once signal on S1 is issued, then signal S1 value will be incremented and it will become 1. Similarly P2 will return and enter the critical section. At this moment, once P2 leaves the critical section, then it has to execute signal on P2, and signal is processed wait on S1. So at first execute wait on S1, it means the value of S is decremented, and then it proceeds to count plus plus. The count value will become 0 because it is incremented, and now it will evaluate the condition if count is less than or equal to 0. Yes, count is equal to, then it will issue signal on S2. It will issue signal on S2, and at this moment signal when it executes for S2, then S2's value will increment and it will become 1. And you can see that meanwhile P3 releases its execution because there is no more busy wait or it. And P2 will also return and execute in its remaining section. Now P3 is free to execute, and P3 first decrement the value of S2 because it was waiting on S2, and now it moves ahead and calls signal on S1. And once it calls signal on S1, then it just increase the value, increment the value of S1, it becomes 1, and it enter in the critical section. After completion in the critical section, it will leave the critical section and signal, then it will call wait, and in wait it will first decrement the value of S1, that will become 0. Next it will increment the count value, that will become 1, and next it will check the condition, that is false, else will be executed, and signal on S1 will be executed, and S1 value will be incremented, and it will then leave it, and now it is in the remaining section. So you can see here that finally the value of these variables are in accordance with the values they were initially they were S1 equal to 1, S2 equal to 0, and count is equal to 1. So this is how counting semaphore is used. Counting semaphore is implemented using binary semaphore.